All right, welcome. Part 2, Chapter 5. We're going to be talking about a different kind of interaction between light and matter that relates to what we call thermal radiation. And before we get into that, I want to discuss with you some of the different types of energy. So, previously in this class, we have developed some tools to help us understand physical phenomena. We talked a bit about motion, laws of motion. We talked a bit about planetary motion. We talked a bit about forces, things like that. And these are all tools. When we understand the physics behind things, we look at physical behavior and we start asking ourselves questions that can be understood through these physical laws. Energy is another type of tool. You can characterize objects as having a certain type of energy, and energy can be converted from one form to another. And so sometimes understanding a physical system is helpful if you can characterize the energy and understand how it transforms between things. So there's lots of different types of this. One really obvious and simple type is kinetic energy. And that's energy that an object possesses because it moves. That's all that's required. If it moves, it has kinetic energy to it. Light, as we learned in the last lecture, has energy. We call that radiative light. And so, that kind of, that form of energy can do things like heat something up, could actually even create a current if you shine on metals and things like that. There are a lot of different types of stored, or we call potential energy. One example of this would be chemical energy. So like food, for example, when you consume food, you get energy out of that. Gasoline has a stored energy it can be used to power your cars. The most common type of potential energy, the one that we'll talk about a bit in the class, is gravitational potential energy. If an object has the ability to fall, it has the ability to release energy. And the potential energy depends on how much mass an object has, the strength of gravity, which is G. We'll talk about that. Oh, actually, we did talk about that already. And the distance an object could potentially fall. So if an object is up on a shelf, we say it has gravitational potential energy because it has the ability to fall and turn that energy into kinetic energy. Things can fall and break stuff. It can break the object itself. So there is a type of stored energy that inherently exists due to gravity. This is going to be something we'll talk about, and I'll just give you an example here. This is something we're going to discuss when we talk about the formation of stars. The formation of stars is best understood when we think about energy. So, stars will start off as this gigantic, cold, dark, diffuse interstellar cloud. Just a giant cloud in space. And that cloud itself is in sort of a balance, just like clouds in the sky. The balance that exists is that the cloud has some temperature to it, not much, but some. And if that could act alone, it would disperse the cloud. The cloud would just dissipate. But if that temperature goes down or somehow is not present, then gravity becomes the more important factor. Every single atom in this cloud is attracted to every other atom. And so that's going to be directed inward. And so these clouds generally have a balance. And if that balance is ever broken and it's in gravity's favor, that will create new stars. So there's like a ton of gravitational potential energy in this cloud. If something triggers the cloud to undergo a collapse or a compression of some kind, gravity can completely take over. That gravitational potential energy gets converted to kinetic energy, at least initially, as things fall towards the center. As things start to fall, they will start colliding with its neighbors, which will increase the temperature of the cloud and give it a bunch of what we call thermal energy. That cloud eventually flattens out into a disk based on momentum. The disk heats up, and eventually planets and our sun will form out of this disk. And we're going to be talking about this phenomenon at least a couple times in this class, once for understand our solar system and once for understand how stars are formed. But it's all in, energy is the main topic when we talk about this stuff. It helps us understand better what is occurring in the cloud. Now, I mentioned thermal energy, and the lecture today we're going to be touching on the topic of thermal energy. So I want to make sure that we understand what we're talking about here. And there's actually several different key terms here that you're going to want to know. There's basically three things that we want to tell the difference between. There is temperature, there is thermal energy, there is heat. So these three things we want to distinguish. They all sound very similar to each other, but they're actually very different. Okay, let's start with temperature. As you can see in the picture here, temperature is basically an average kinetic energy of the particles in your system. So say, for example, you have a glass of hot water and a glass of cold water, and you dip your finger into those. Okay. With the one that is warmer, the water molecules are bouncing into your hand much more vigorously than in the lower temperature one. You detect that, and you know that that means the temperature is higher for that object. But ultimately, when we talk about temperature on a microscopic level, it has to do with the atoms or molecules bouncing around. And the higher temperatures, they bounce around a lot faster. And that's really the basics of what temperature is all about. Now, thermal energy is a little bit different. It does involve temperature for sure, but it also involves the amount of substance that you have. So thermal energy is sort of a measure of all of the kinetic energy of the particles in a substance. So it depends on temperature and it depends on density. And this illustration is really great for understanding the difference between the two. The oven here at, say, 400 degrees is significantly hotter than the pot of boiling water. The atoms in the air are moving around much faster than they are in the pot of boiling water. If I were to stick my hand in the oven for, say, 5 seconds, it may be a little uncomfortable, but I'm going to be fine. If I stick my hand in the pot of boiling water for 5 seconds, I'm going to have a very bad day, and I'm probably going to have to go to the hospital. But, it's all for science, so, well, I don't know. But the reason why what's happening here with the pot of boiling water is that while an individual molecule may hit my hand less vigorously than the one in the oven, the collisions are happening way more frequently because the water is dense and the collisions are taking place constantly. And when enough collisions are going to take place, that will damage the cells of my skin. That's exactly what a burn is. It's these things bumping into your cells so hard that they destroy the cells. Great illustration of thermal energy. We say the pot of boiling water has way more thermal energy than the oven does. That's the biggest difference. Now, aside from these two concepts is the concept known as heat. Heat is a flow of energy. It's a flow of energy. It's a transfer. So an object that is hot and an object that is cold, right? There's a temperature difference. And if they're put in contact, that energy will flow from the hot substance to the cold substance. That process is what we call heat. A really nice illustration of heat is shown in this video here, which I'm not going to show you the video because YouTube will freak out and try to strike my channel. So I will put a link somewhere in either the discussion thread or maybe I'll embed it in the description of the video here. But this is a demonstration of the space shuttle tiles that are put onto the space shuttle when we had it, which we don't anymore. And what's happening here is they stick these two blocks in an oven that puts them to around 2,000 Fahrenheit or so. And they take them out of the oven, and this guy is able to grab them with his hands. And the reason why he's able to do that is while they have a very high temperature, and they're a solid, so they have a decent amount of thermal energy to them, they don't transfer that energy very well. They have very low thermal conductivity, we say. The heat transfer is low, very low. He actually has to grab them around the edges just to be safe, because after a little while, heat does start to dissipate. But that was the purpose of the tiles, is that upon re-entry of the space shuttle, it gets insanely hot as it falls through the air. And you don't want that heat to get into the cabin where the astronauts are. So the bottom of the space shuttle has a large, basically this giant set of armor that's made up of this stuff, so that they heat up, but they don't transfer the energy into the shuttle itself. And so it was meant to protect that shuttle. But that's a nice illustration of heat, because most things you touch, when you feel things, like, touch some metal, it feels colder generally than other things you might touch, but that's due to heat transfer, not necessarily due to the temperature differences. If you're in a room with something, everything's basically at the same temperature. All right, let's get back to the lecture. All right, so now for temperatures, we're used to Fahrenheit because we live in America and the F stands for freedom. But most places don't use Fahrenheit for their temperature scale. They use Celsius. Both are somewhat arbitrary systems, kind of designed around water and how many divisions there are between freezing and boiling. After these systems were developed, though, physicists realized that there actually is a coldest temperature, and it would make sense to just put the coldest temperature at 0 as opposed to putting 0 in other places on the scale. And so in the sciences, we use kelvins to do this. Now, the problem with kelvins is just they're not as familiar. But most of the temperatures we're going to talk about in this class are really high. And so it kind of doesn't matter what temperature scale I use, because the numbers are just really high and you're not used to any of these things. But I will say this, if you do want to try to make a comparison between kelvins and Fahrenheit, if your temperatures are sufficiently high, like in the thousands, you could double a Kelvin temperature, and it's roughly what it is in Fahrenheit. Okay, roughly. Okay, it needs to be in the thousands. As you can see here, that doesn't work with the lower temperatures. But when you get to a higher temperature, it's roughly 2 times, Fahrenheit is 2 times larger. If you want to be a little more technical, it's 1.8, by the way, but whatever. So room temperature is around 300 Kelvin. That's like room temperature-ish stuff. All right. So just to recap the stuff we talked about last time, just to recap real quickly. We talked about atoms. We talked about them having protons and electrons. They're attracted to each other. The electron, however, cannot be wherever it wants to around the proton. It's sort of restricted to different levels inside the atom. These levels are unique to each atom. So the transitions that the electron can do are also unique. The electrons are allowed to jump to different levels if they get the exact right amount of energy to do so. They jump up to higher levels. That's called photon absorption. They could jump down by releasing light. That's photon emission. We talk about the various wavelengths that correspond to a particular atom as the fingerprint of the atom, because it is unique. Every atom has its own unique set of lines that work for it. So it is like a fingerprint in a way. When we look at the spectrum of a star, we look for the fingerprint, and we know that particular atom must be in that star. So in the picture here is a spectrum that is showing hydrogen absorption lines. This first line in the red is called the Balmer alpha or H alpha line. It's at 656.3 nanometers. This line here is the 286, the other one's the 343. This red line is the transition from level 2 to level 3. This blue line is 2 to 4, and the last line's 2 to 5 here. That's the only lines that you can really see in the visual spectrum. There are more lines, but they lie outside in the other regions, either ultraviolet or the infrared. And I was showing you this analog spectrum before, where you just see the rainbow of colors and certain dark lines. The picture on the bottom of this is digital spectra. It's a graph of wavelength and intensity. So the colors aren't there. The colors are instead replaced with the actual wavelengths they correspond to. And then we get information that we didn't have before, which was intensity, how bright the light is at different wavelengths. So the absorption lines appear as these spikes, these big drops in intensity. Again, because the hydrogen atoms are present and they're taking the light away. And, this is the more modern way to display spectra, digitally, wavelength and intensity. So you might see that. I don't show that too often, though, because it sometimes hurts people's brains. So take one notice here with something, though, and I'm going to come back and explain a bit. Notice how this star has a lot more blue light than red light. That means something. Okay, I'll come back to this slide in a little bit and ask you this question again. You may know now, but you probably don't. But in the next 10 minutes pass, you will know the answer to that. All right, so here's the second way. There's a second way that you can excite an atom. One was photons, by having them hit the atoms and absorb. And the second way to do this is through particle collisions that occur from thermal motion. So, having a temperature means that your molecules or atoms or whatever are bouncing around. And that means they're going to bounce into each other. Bouncing into each other can transfer energy. And if the bounce is just right, the electrons can be kicked to higher levels. Eventually they'll kick back down and they release light. That exact mechanism, the exact mechanism behind that, whereas you have, atoms of not just one speed, but kind of a range of speeds, they can collide with other atoms and cause the atoms to emit light. It's kind of complicated. In fact, it's so complicated that an entire new branch of physics had to be created about 100 years ago to explain it, and that's called quantum mechanics. Quantum mechanics is interested in the dealings of atoms, and you need to know exactly what's going on inside of an atom to understand this phenomenon here. So we're not going to get into that, okay? The basic question that was trying to be answered by quantum mechanics was this: why do objects glow when they're hot? I mean, that was really it. That was the question ultimately. Why do objects glow when they're hot? Well, again, like I said, it's another way to excite atoms. It's through all these collisions. You don't need to know the mechanism. All you need to know is what the result is. For an object that undergoes this, and this is basically true of any object that is dense and has a temperature, which is most things, the result is a thermal radiation spectrum. It's light emitted across the spectrum. Here are some examples of that. Now, like I said, any object that is considered to be relatively hot and dense. And when I say hot, I don't really mean hot. I mean just have a temperature. Wherever you're listening to right now, wherever you are, all around you, objects are emitting thermal radiation. Now, hopefully, not enough that you can see them glow, because if that is, you should pause the video and take care of that. Because, normally things are, like right now, I have this computer in front of me here, this laptop. It's not glowing to me, but it has a temperature and it's dense, and it's producing thermal radiation. Everything's doing this. Now, the objects that you see in the picture here, these are really hot things. 5,000, 6,000, 7,000 Kelvin. We're talking about things that are around 10,000 Fahrenheit or larger. So this is not something you commonly see unless you actually literally see a fire or something like that. But look at what's going on with these objects. They're all emitting a continuous spectrum of light. There's ultraviolet here, visual, infrared. It drops off on the edges, but there's more on the edges. And while they all emit basically a continuous emission or a rainbow of colors, they do so slightly differently based on their temperature. The one at the bottom has a peak wavelength around orangish, reddish light. And the object will actually look kind of orangish red because of this. But as the objects heat up, they emit more light overall, and this peak starts to shift. Here it's around green light. If I get up to the 7,000 Kelvin object, you can see there's more light overall, and the peak is shifted to even shorter wavelengths. This object is peaking around the blue part of the spectrum. And this object is going to look blue as a result of that. Now the one in the middle here, you might think, well, that one's going to be green, right? Actually, no, it's not green. It may have a slight greenish tint to it, but when you're in the middle here, there's almost equal amounts of all types of light, and so this kind of looks more whitish in appearance. So, but otherwise, yeah, it might have a small green tint to it. Our sun is in between these two, by the way. The peaks are on yellowish light. So the sun has a slight yellow tint to it. It's not like mustard, but it's a slight yellow tint to it. Everything does this. I mentioned the laptop I'm working on right here does this, but the temperature of the laptop would be insanely small, and so the level of light is tiny. You wouldn't be able to really see much of anything there. But that's why when you see things in the infrared, like through infrared cameras or things like that, you see things glow. It's because you're detecting the heat signatures in the infrared, and because the objects have a lower temperature, they peak in the infrared. That's the idea. Okay. By the way, let's go back to that picture now. There's more blue light than red light. This object is a considerably hot object. In fact, the peak, we don't even know where the peak actually is because it just keeps going up. Probably peaks somewhere in the ultraviolet. So these objects here are probably hotter. This object here is probably hotter than the three things that are here because the peak appears to be somewhere in the ultraviolet here. So anyway. All right, so those two properties that I discussed with you are two laws of thermal radiation. The first one is the Stefan-Boltzmann law, and the second one is Wien's law. You want to understand the concept, and there is a little bit of math, don't hate me, to this stuff, okay? But I'm going to provide very detailed examples so that you won't hate me as much, okay? The Stefan-Boltzmann law, from a conceptual standpoint, is pretty straightforward. Hotter objects are brighter objects. That's it. Hotter is brighter. That's all you got to know for the concept. For the equation, the emitted power, which is basically how much light's coming out of this thing, how much light is coming out of this thing is equal to sigma, which is a constant, 5.7 times 10 to the minus 8, times your temperature to the fourth power. Temperature must be in Kelvin. So there really is only one variable here, that is the temperature. The temperature of the object determines exclusively how much power is emitted, how much light comes out of the object. Wien's law has a slightly more complicated concept to it, but let me go back to the pictures here so you can see that. See these peaks? What Wien's law says is as the object gets hotter and hotter, this peak will shift to shorter wavelengths. The peak is where most of the light, or at least the most amount of light, is being emitted in these objects. So the peak of the thermal radiation spectrum will shift to shorter wavelengths when the temperature increases. So there's an equation here. The equation is the peak wavelength is approximately 2.9 million divided by the temperature. If you know the temperature, you put it into the equation here, 2.9 million over your temperature, tells you where that peak lies. Okay, tells you where the peak lies. Let's look at an example. Say we are dealing with a 2000 Kelvin object. What would be the emitted power and what would be the peak wavelength? So I take my sigma value here. That never changes. It's always 5.7 times 10 to the minus 8. You put your temperature in here. Raise it to the 4th power. Make sure that's kelvins. What we get out of this when you put this in your calculator, 9.1 times 10 to the 5th. Watts per square meter. That's almost a million. This object is 2000 Kelvin, which by the way is not very hot when it comes to stars. Our sun is around like 5,800 Kelvin or something like that. And this is significantly cooler. But every square meter, which is like a 3 foot by 3 foot window, emits 1 million watts. I mean, that's crazy, right? But that's true. Wien's law, 2.9 million divided by 2,000 is 1450 nanometers. Now, if you remember from the previous lecture, this is beyond 700. So this actually is infrared light. So this object is cooler, and it wouldn't be very bright in the visual spectrum. Apparently, it's going to be bright around the infrared. It's bright around the infrared. Okay. So you will have examples that you'll need to do in your homework. Okay, what I recommend you do is punch these things in your calculator in here and verify that you get these answers. When you go to do your homework, I'm going to give you a different temperature. All you got to do is replace the 2000 in these two equations with that temperature. And as long as you worked out these two examples here correctly with your calculator, you should be able to do the examples in your homework with your calculator. Okay, so it's literally just a matter of changing the 2000 to a different number. That's it. Okay. Here's another example of Wien's law. You can do kind of the opposite with it. So instead of trying to find the peak wavelength, you could actually try to find the temperature if you have the peak wavelength. And in fact, this is the way that we normally speak about Wien's law, because we can observe a peak wavelength. That's something we can see in our observations. And then that directly relates to how hot the object is. So that's how, at least in practice, it's used. But say we find an object and we realize it's very hot. Like say, for example, that one I showed you way back here, right? This thing right back here. Oh, no, what did I do with it? Okay, here it is. So say, we want to study this object, and we just discovered that, like, this may not actually be the peak right over here on the left. It may actually continue to go up. So we get out our ultraviolet telescope or ultraviolet satellite, and we observe the object. And sure enough, we discover that it actually does have a peak that's not around 400, but it's around 150 nanometers. That's well into the ultraviolet. So let's go ahead and put that through our equation. 2.9 million divided by 150 is 19,000. So this object is 19,000 Kelvin. It is significantly hotter than the examples I showed you. And that's not uncommon for a star to be that hot. Fahrenheit-wise, it's around, that would be around like 36, 35 or so Fahrenheit. So pretty hot. All right. Yeah. Okay. So what's going on with the sun? The sun is a hot, dense object. The sun has the temperature in the mid 5,000s Kelvin. So I have this picture here that shows what the sun is doing as far as its thermal radiation spectrum is concerned. The dark line that you see here, that corresponds to the level of light that's being emitted due to thermal radiation by the surface of the sun. So what we call the surface, the hot and dense region, is that dark line. We cannot see that dark line because that light has to get through the atmosphere first. Once it gets to the atmosphere, there's a series of absorptions and emissions that can take place. And what comes out is the stuff that is colored in yellow. Colored in yellow. Now, once that light gets out of the atmosphere, it starts to travel through space. Now, assuming there's nothing between us and the sun to alter that light, which, by the way, can happen if we talk about distant stars, but not our sun, which is our neighbor here. Eventually, it has to get through our atmosphere then and reach the ground. And once it gets through our atmosphere, it becomes the red stuff here. Now, we know exactly what's happening in our atmosphere. And so at the telescope, we can always correct this and bring it back to the yellow. We can always do that. But this is what our sun looks like. Okay. It peaks in the visible part of the spectrum. It apparently has a little more visible light coming out of it than it had from the surface. It's because some of the infrared and ultraviolet got wiped out a little bit here. But, this is what our sun looks like. And you can have a picture like this for every star. What's going on the surface, what gets out, what gets to the Earth. And so this is how we're studying our objects here. The visual spectrum doesn't look too different, honestly. The infrared looks pretty different, though. The infrared has a lot of big chunks taken out of it due to water vapor and carbon dioxide and other greenhouse gases. So that's neat. Okay, now, poetry. Did you even think you'd have some poetry today? Star A is red, star B is blue. Assume they're basically the same size. Which one will have a higher surface temperature? What do you think? Well, the answer here is B. Right? That's Wien's law. If the object looks blue, then it's primarily emitting blue light. So it's a hotter object. Star A is red, it's cooler. That's true. You go outside, you look at the stars in the sky. If you see a distinctly red star, it is on average cooler than the other stars in the sky. If you see a blue one, it's usually a bit hotter. So now you know. All right. Star A is red, star B is blue. Assume that they're basically the same size and located the same distance from the Earth. Which star has a larger apparent magnitude? What do you think here? Now, a couple things to think about here. What does it mean to say a star has a larger apparent magnitude? We covered this back in chapter 2, which was a few weeks back, but this is a tricky one. The answer here is A. All right, we established in the previous question that A is a cooler star. And the Stefan-Boltzmann law tells us that a cooler star will not be as bright. A star that's not as bright has a large apparent magnitude. So when I said which star has a large apparent magnitude, I'm really asking you the question, which star is fainter? Which star is fainter? And that would be A. A is fainter because it's cooler, all things equal. Okay. All right, fantastic. So by the way, I mentioned these things about the colors. Blue is hotter, red is cooler. You got to remember the rules about this, though. Let me go back. The surface of a star is hot and dense enough to produce a thermal radiation spectrum. If you're trying to identify colors with temperature, you have to make sure that you are dealing with a dense enough object. Let me give you an example. If you have an electric stove and you crank it on high, you'll notice the coils start to glow kind of orangish red. That's thermal radiation because the coils are hot and dense. Now, they don't get to thousands of Kelvin. They probably get to hundreds of Kelvin, but it's enough that you actually can start to see the glow of the object. That's thermal radiation. If you have a gas stove and you crank it up and the flames are going and they look blue, that blue is not thermal radiation because the flames are not dense. That's light emission. That's stuff we talked about in the last lecture. Okay, the question is always, is it dense or is it not? Okay, if it's not dense, if it's a gas, the colors are due to emission lines as opposed to thermal radiation. Okay, most people haven't seen things that glow because they're really hot. Obviously, like the electric coils of a stove, yeah. An actual fire, like the embers of a fire, not the flames, but like if it's wood and you see the wood glow, That's thermal radiation. And most of the time it looks just orangish red. You've never seen an object so hot that it's blue, other than look it up into space and say, oh, that's a blue star. But nobody's ever seen an object so hot that it's blue. Because if you get to temperatures that are that high, you probably won't be alive to tell me about it. Sad story. All right, let's get back to this. Well, look at this. There's Betelgeuse in Rigel. This is the constellation of Orion. There's that belt right there. When you look up at Orion, Betelgeuse is very clearly red, and Rigel is very clearly blue. And you know why now. Betelgeuse is cooler than Rigel. That's it. You don't get too many colors, though, for stars. It's kind of either red, blue, or white. Because, like I said, when you're peaking in the middle, you kind of get an equal blend of colors. So you don't really see much of anything there in terms of a color. Right? Now, here's a question for you. Let's do some science. This is some real science right now. Now, Rigel's hotter because it's blue. That's Wien's law. Now, I'll tell you that Betelgeuse and Rigel are very similar in distance from us. Very similar in distance. We look at Betelgeuse, and the question you could ask yourself is this: shouldn't it be fainter than this? I mean, that's Stefan Boltzmann law. Temperature to the fourth power. That's a huge exponent. If you have an object that's, say, twice as hot, it should be 16 times brighter. So we have a kind of an issue here with Betelgeuse. It's red, it's cooler, but it doesn't appear to be that much fainter than Rigel. It's kind of hard to tell in the image here, but no, Betelgeuse should not be this bright. So the question you want to ask yourself is, what's going on here? Now, you don't know the answer to this question yet, but you can try to take a guess right now. Think about it. They're the same distance from us. Rigel's much hotter, but it's not that much brighter. What do you think's going on with Betelgeuse? What do you think's going on with Betelgeuse? Think about it for a little bit. I'll tell you right now, though. You want to pause the video if you want to think about it. The reason why Betelgeuse is so bright is because it's larger. It is very large. Rigel may be 3 to 4 times larger than our sun. Betelgeuse is like 500 times larger than our sun. And even though you're cooler, having all that surface area allows you to emit a lot more light. So we're starting to infer some other things about our objects. Now that we understand about the temperatures of objects, we start to see some odd things, and we start to think about what that might mean. And in this case, we can tell that Betelgeuse must be a big star, because it should not be this bright. All right, science. Now, everything we talked about in these 2 chapters here can be summarized very nicely in what is known as Kirchhoff's laws of radiation. Now, your book has these, but I think, if I remember correctly, they put them in a different order than I have them, which I don't really care for. So I'm going to put them in a different order myself, just because I think it's more logical to do it this way. All right, the first law is this. The first law is about thermal radiation. A solid, liquid, or dense gas, basically just solid or liquid. Your gas has to be crazy dense for this to work, but anyway. Excited to emit light will radiate at all wavelengths and produce a thermal radiation spectrum. So you just need a hot, dense object to do this thing. What's being illustrated in the picture here is a traditional incandescent bulb. Traditional light bulbs have a filament made of a very thin metal, usually it's tungsten, and a current passes through the filament and it causes the filament to get extremely hot, and because it's a hot, dense object, produces a rainbow of colors. If you could look at the light bulb with a spectrograph that can disperse the light, you're going to see a rainbow of colors. Which, by the way, is a good example of why we are encouraged to not use traditional incandescent bulbs, because they are a waste of energy. I mean, if you think about it, it's kind of almost barbaric to use a light bulb to light a room because you're just heating up an element, little piece of metal, and you're just spewing out all forms of radiation. And you don't need all that, right? There's a ton of infrared radiation coming out of this light bulb. What does that do? It just burns your hand. It doesn't help you see in the room. So the LEDs that we have, or the the fluorescents, CFLs, and all that stuff, those work on emission lines, not thermal radiation. So they only spew out certain wavelengths of lines, and therefore can conserve a lot more energy. So that's nice. Law number 2 is about absorption. So you take the same setup from the previous example, and you surround it with a cool gas, and you look at the light bulb again. Now you're looking at the light bulb through the gas, though. So you'll see the rainbow of colors because you're still looking at the light bulb. But now there's certain dark lines that are going to appear. Those dark lines correspond to transitions that work for those atoms. So if it's a particular gas that you're familiar with, you should see the pattern of lines that correspond to it. So, that's what the absorption is going to look like. You're just basically observing the interaction that light has with the gas that's around it. And then you take the same setup, and instead we point it at the gas now and not the light bulb. We just want to see what the gas is doing. So you're going to get a dark background because you're not looking at the light bulb anymore. But when you look at the gas, the wavelengths that were previously absorbed are now back because now you're looking at an emission taking place. And so you should be able to see the wavelengths that were missing before. That's line emission. So those 3 things kind of summarize everything we did in this chapter. Thermal radiation, absorption lines, emission lines. And this one example here kind of encapsulates all of them. In fact, this applies directly to studying stars. The star is like a light bulb. The atmosphere of the star is like that cool gas around it. When we look at a star, we're always seeing a thermal radiation spectrum initially, and then the absorption lines that sit on top of those. And if you could somehow isolate just the atmosphere of the sun, you would see a bunch of emission lines, which you might remember seeing back in chapter 4. We talked about eclipses, and in one of those pictures, I showed you a total solar eclipse, and all around the edge of the moon was this pinkish, purplish color that was the emission lines from the atmosphere of our sun. You might want to look back on that during the solar eclipse part of the chapter 4 material. You could see that. Normally it's very hard to see that stuff, but the moon nicely blocks the surface so you're able to see those things. But that's why we're interested in all this stuff, because this is how stars are going to look. Stars have an absorption spectrum to them. And so we need to understand that. All right, so let's do an example here that kind of puts some of these ideas into practice. This is the part of the Eagle Nebula, which is a smaller part of a larger picture that you might be familiar with called the Pillars of Creation. Very famous Hubble image showing these 3 pillars that appear to be rising up from something, but that's actually not taking place. In this example here, we have another gas pillar. And every time we see these gas pillars, we know that there's some brand new stars that are going to start to show up here. But the visual wavelength picture that we would take is not really going to reveal that. The visual wavelength picture that's taken here is the red stuff. And that kind of defines the structure of the pillar. We can see, where the gas is located by the optical emission from hydrogen. That's all the red color. The problem with that, though, is that you can't tell what's going on, though. Like, it's not clear where the stars are, because there are a bunch of stars forming here. So we switch to the ultraviolet. We switch to ultraviolet and take another image. The idea here is that those brand new stars that are starting to show up are going to start to shine light on the nebula that surrounds them. It's going to take that cool gas and it's going to turn into a warmer gas, and that gas will start producing emission lines. So we switch to the ultraviolet as a means to look for those emission lines, and that's the blue color. So when you look up near the top here, we can see there's a lot of blue going on up here, and in particular, this one spot in the upper left shows a lot of intense blue color here. And that must mean the stars are inside here and they're trying to get out. And that's the source of the radiation. We would follow this up with an infrared image, because infrared images help you see through these clouds, which you don't know yet, but I'll talk to you later about that phenomenon. So that's kind of an interesting thing to think about here. And so the combination of all these different wavelengths gives us different pieces of information that can help piece together the location of these new stars, and then the infrared tells us what kind of stars are actually present there. So it's kind of neat. All right, we have one last topic here before we wrap up chapter 5. And that is how light can be affected by motion. And we call this the Doppler effect. A Doppler effect actually occurs between anything that emits waves. It could be sound. It could be light. It could even be like, say, motion on a body of water, where you see ripples in the water. You're probably most familiar with this due to sound. So in the example they show in the upper left here, we have a fire engine that's blaring its engine, the siren. And for a person that stands in front of the fire engine, they're hearing a different sound than the person that is on the other side. As the sound waves are emitted, they compress in the direction of motion and they stretch out opposite the direction of motion. And that changes the wavelength and the frequency of the sound then. The person that stands on the left will so if you can see from the wavefronts here, the wavelengths are shorter. That means the frequencies are higher. This person is going to hear a higher pitch siren. The person on the right is hearing a lower pitch siren. You might have experienced this because when a fire engine or ambulance suddenly passes you, say you're standing on the side of the street and there's a emergency vehicle driving by you, you hear that high pitched sound, and as soon as it passes you, it kind of goes pew, and then it gets to a lower pitch. And that is the shift that's occurring due to the Doppler effect. Now, this also happens with light. If a light source moves towards you, it can change the wavelength of the light. We call it a blue shift because the wavelengths become shorter. They shift to the blue end of the spectrum. It doesn't mean the object looks blue. It doesn't mean that. It just means that the wavelengths shift to shorter wavelengths, and the short end is what we call the blue end. We have a red shift, which occurs if an object moves away from you. And that stretches the wavelength out. And again, the object doesn't necessarily look red. It could. Not necessarily, though. It could look red, but the light is stretched out. And so it becomes longer. And if you can measure how much this is either compressed or stretched out, then you actually can come up with how fast it's moving toward you or away from you. This equation up here illustrates that. On the left-hand side is a ratio of how much the wavelength has changed compared to what it originally was. And the other side is a ratio that has the speed of the object over the speed of light. So knowing how much your wavelengths have shifted from what it ought to be can help you measure how fast the object moves. And, back in the stuff we talked about before, we have a pretty good idea of where all these things lie. For example, the red line of hydrogen is normally 656.3 nanometers. But as we orbit the sun, we can watch a nearby star and actually see our own motion in that star. As the Earth in the solar system, as it's orbiting, moves toward the star Arcturus, we detect that line at a slightly shorter wavelength. As we get to the other side of the sun, and then we're now moving away from Arcturus, we can detect a slightly longer wavelength. The shift in wavelength is just basically this small little difference here, which looks like it's only a tenth of a nanometer. But you put that into the equation, and you can get roughly a speed for how fast things are moving. And this is for this is about a nanometer, a tenth of a nanometer, which would correspond to about 30 kilometers per second or so, which is how fast our Earth does move as it travels in its orbit. But, for any kind of object, it could be due to our motion, it could be due to its own motion, but seeing these shifts reveal what that is. You also can determine rotation. And I know there's a lot going on in this picture here, but the only thing I really need you to get out of this is that as objects rotate faster and faster, these lines that we see become broadened. They become thicker. The thickness of the line is due to the fact that as the object rotates, one side is always moving toward you and one side is moving away from you. So there's a natural sort of thickness to all the absorption or emission lines. As the object rotates faster and faster, that kind of spread increases. And you can see down here the difference between narrow lines and broad lines. The one on the bottom is clearly rotating very rapidly compared to the one on top. And we can detect those things, and we can determine how fast things spin as a result of that. All right, last question for you here. And we'll wrap up chapter 5 and we're ready to get into the new stuff, chapter 6 and beyond. In theory, and I cannot emphasize that enough, in theory, if you travel fast enough in your car toward a streetlight, which of the following could you achieve? So think about that for a moment. This is a ridiculous question, but still there's some benefit to thinking about it. The answer here is you can make a red light turn green. Because if you're moving toward the light, that's a blue shift. And so wavelengths can move towards shorter wavelengths, green shorter than red. This could happen. Option B would be a red shift, taking green and turning it to red. Now, before you think, oh, I could use this argument in court, right? I can get out of a ticket because I'll just say, oh, wait, no, you can't do that because you're going to admit that you're going way too fast. It looked green to me because I traveled so quickly. Well, if you actually look at the wavelength difference between red and green, it's about 100 nanometer difference. Red's around 650. You could put green around 550 or so. So it's about 100 nanometers. Compared to the wavelength of red light, which is 650 nanometers, if you do the equation here, you get that you would have to travel at about 1/6 the speed of light, which you should not admit in court because I can't imagine what the fine would be for that. It probably would be pretty big. So, but that's neat. That's neat. You could do that. Technically, if you travel that fast, yeah, it would happen. You would look at the light, and the top portion that's supposed to be red would just look green to you. Okay. Now, here's an interesting idea. Well, because say you did it. You blew through the light, then you decided to look behind you at the light on the other side. What do you think you'd see? Think about that for a moment. Would you see red? Well, no, because now you're moving away, and that would be a red shift. So what's longer than red? Infrared. So you would see nothing because your eyes can't detect the infrared. The light would be shifted into the red part of the infrared part of the spectrum, but you can't see the infrared. So you look behind you, and that light would look like it's out. It's not working, but it's actually the infrared. All right, that wraps up chapter 5. See you in chapter 6.